On November 15th, 2025, astronomers around the world turned their telescopes toward a faint streak of light moving through the constellation Cancer, watching as something strange began to happen. The object they were tracking, a comet called 3I Atlas, started showing a tail that pointed the wrong way. Instead of streaming away from the sun like every comet tail you have ever seen in pictures, this one aimed straight at it. Scientists call this an anti-tail, and seeing one form in real time is like watching nature break its own rules right before your eyes. What makes a comet grow a tail that points toward the sun instead of away from it? Why does this visitor from beyond our solar system behave so differently from the icy wanderers we know? And what can this backward-pointing streak of dust teach us about the hidden worlds that drift between the stars? Stay with me, and we will walk through one of the strangest shows the night sky has given us in years. Let's start with what we know for certain. 3I Atlas is not from around here. The 3I in its name stands for Third Interstellar Object, meaning it is the third thing we have ever confirmed came from somewhere beyond our Sun's family of planets. It was first spotted on August 28, 2024, by the Atlas Survey Telescope system in Hawaii, which scans the sky every night looking for anything that moves. At first, astronomers thought it might be just another comet from the outer edges of our solar system, one of the millions of icy chunks that orbit far beyond Neptune. But when they calculated its path, they realized something remarkable. This object was moving too fast and on the wrong angle to be bound to our Sun. It had come from interstellar space, the vast darkness between star systems, and it was just passing through. Picture this. Imagine you are standing in a big field on a summer evening, and fireflies are floating around you in gentle loops. Those fireflies are like the comets and asteroids that belong to our solar system. They stay nearby, circling the same small area, bound by invisible threads to the place they were born. Now imagine a bird flying straight through that field, cutting across all those looping paths without slowing down or curving. That bird is like 3I Atlas. It is not part of our system's slow dance. It came from somewhere else, and after its brief visit near our Sun, it will fly back out into the cold space between stars, never to return. Scientists have measured the speed and direction of 3I Atlas very carefully. Records show it is travelling at about 34 kilometers per second relative to the Sun. That might not mean much to you yet, so let's put it another way. If you could drive a car that fast, you would cross the entire United States in less than 2 minutes. This comet is racing through our neighbourhood faster than almost anything that belongs here naturally would move. Its path is what scientists call hyperbolic, which is a fancy word that means it is not trapped in an oval orbit around the Sun. Instead, it swooped in from deep space, curved around the Sun like a slingshot, and is now heading back out the way it came. We will never see it again. Now here is where things get interesting. In early November 2025, as 3I Atlas continued its journey away from the Sun, something unexpected started to appear. Astronomers using telescopes in Chile, South Africa and Arizona began noticing a faint spike of light extending from the comet's bright centre. But instead of pointing away from the Sun like a normal tail, it aimed straight back toward it. Over the following days, this anti-tail grew longer and brighter, until by mid-November, it stretched across a noticeable portion of the sky. Some observers reported seeing it extend for nearly half a degree, which is about the width of the full moon as seen from Earth. Let me explain what an anti-tail actually is, because the name makes it sound more magical than it really is, even though it is still pretty amazing. Every comet is basically a dirty snowball made of ice, frozen gases, and rocky dust all clumped together. When a comet gets close to the Sun, the heat makes some of that ice turn directly into gas, a process called sublimation. As the gas rushes away from the comet's surface, it carries tiny dust particles with it. This creates the beautiful glowing tail we usually see streaming behind the comet like the train of a wedding dress. Most of the time, that tail points away from the Sun because of something called solar wind and sunlight pressure. The Sun is constantly blowing out a stream of tiny particles and energy in all directions, like an invisible breeze filling the entire solar system. When this wind hits the gas and dust coming off a comet, it pushes them away from the Sun. That is why comet tails always point away from the Sun, not behind the comet in the direction it came from. If a comet is flying toward the Sun, its tail points backward. If it is flying away from the Sun, its tail points forward. The tail follows the solar wind, not the comet's motion. So what is an anti-tail then? It turns out that when a comet releases dust, not all of those particles blow away quickly. The heaviest dust grains are too big and heavy for the solar wind to push them very fast. Instead of streaming away in a long tail, they spread out slowly along the comet's orbital path, creating a flat disk or sheet of particles. Imagine dropping breadcrumbs as you walk along a trail. Those crumbs do not fly away, they just sit where they fell, marking your path. That is similar to what happens with the heavy dust from a comet. Now here is the clever part. From Earth, we see this disk of dust from different angles, as both Earth and the comet move through space. Most of the time we see the disk edge on, or at an angle, and it just looks like a faint blur around the comet. But sometimes we happen to pass through the exact plane where that dust disk is sitting. When that happens, we suddenly see all those dust particles lined up in a narrow spike that appears to point back toward the sun. It is not really a tail pointing at the sun. It is more like looking at a dinner plate edge on and seeing only a thin line, when from above you would see the whole round plate. The dust in an antitail is still there all the time, quietly orbiting near the comet's path. We just do not usually see it because of the angle we are looking from. When Earth's orbit carries us through the right spot, boom, the antitail appears like a surprise laser beam in the sky. For 3i Atlas, that special alignment happened in mid-November 2025, giving us one of the clearest views of an antitail from an interstellar visitor that we have ever had the chance to study. Before we move on, let's recap what we have learned so far. 3i Atlas is a comet from interstellar space, the third confirmed visitor from beyond our solar system. It is racing through at incredible speed, on a path that will take it back out into the darkness between stars. In November 2025, as it moved away from the sun, a rare antitail appeared, created by heavy dust particles left along its orbital path. When Earth passed through the right angle to see that dust disk edge on, it looked like a tail pointing straight at the sun. The appearance of this antitail was not just beautiful, it was scientifically valuable. When you see dust from a comet lit up by sunlight, you're looking at physical evidence of what that comet is made of. Different types of dust particles reflect light in different ways. By studying the brightness, colour and behaviour of the antitail, scientists can learn about the size and composition of the dust grains, which tells them about the comet itself. For an object that came from another star system, every detail matters. One team of researchers at the European Southern Observatory in Chile used a powerful telescope to take detailed images of the antitail every night for 2 weeks. They measured how the brightness changed along its length and how its shape evolved over time. Their early findings, shared at an astronomy conference in late November, suggest that the dust particles in 3i Atlas are similar in size to those found in comets from our own solar system. Most of the grains seem to be between 1 and 100 micrometers across. To give you a sense of scale, a human hair is about 70 micrometers wide, so we are talking about dust particles ranging from much smaller than a hair to about as thick as one. This similarity is fascinating because it suggests that the process of making comets might be pretty much the same everywhere in the galaxy. Whether a dirty snowball forms around our sun or around a star 50 light-years away, the basic ingredients and the way they clump together seem to follow the same rules. It is a bit like discovering that the recipe for making bread is the same in countries all over the world, even if the bakers have never met each other. But 3i Atlas has given us more than just a pretty antitail. In the months before the antitail appeared, scientists used some of the world's most advanced telescopes to study the comet's composition. The James Webb Space Telescope, which orbits Earth and can see types of light invisible to human eyes, pointed its instruments at 3i Atlas in September 2024, shortly after it was discovered. What Webb found was both expected and exciting. The telescope detected clear signs of carbon dioxide, water vapour and carbon monoxide coming off the comet as it warmed up near the sun. These are the same chemicals found in comets from our solar system, but seeing them in an interstellar visitor confirms that comet-making materials are common throughout the galaxy. Let me break down what those chemicals tell us. Carbon dioxide is what you breathe out and what makes soda fizzy. In space, it is frozen solid at the incredibly cold temperatures far from any star. Water vapour is just steam, the gas form of water. Carbon monoxide is a simple molecule made of one carbon atom and one oxygen atom stuck together. All three of these substances are frozen into the icy body of the comet. As the comet approaches the sun and heats up, the ice does not melt like ice cubes in a glass. Instead, it goes directly from solid to gas, and that escaping gas is what telescopes like Webb can detect. Finding water on 3i Atlas is particularly interesting because water is essential for life as we know it. Every interstellar comet we have studied so far has contained water, which suggests that water is abundant throughout the galaxy. If comets regularly carry water between star systems, they might have helped deliver water to young planets billions of years ago. Some scientists think that much of Earth's water might have arrived on comets and asteroids that crashed into our planet when it was young and still forming. If interstellar comets like 3i Atlas have been wandering the galaxy for billions of years, splashing water onto planets here and there, they might have played a role in making places like Earth hospitable to life. Now picture this. Billions of years ago, when our solar system was just forming from a spinning cloud of gas and dust, interstellar comets were probably flying through all the time. Some of them might have been captured by the sun's gravity and stayed, becoming part of the collection of icy bodies we see today in the outer solar system. Others passed through briefly, maybe even colliding with the young Earth or other planets. These ancient visitors could have delivered not just water, but also organic molecules, the carbon-based compounds that are the building blocks of life. 3i Atlas is helping us understand that this process was not unique to our solar system. It happens everywhere stars and planets form. Let's step back for a moment and think about how rare and special it is that we can study objects like 3i Atlas at all. For almost all of human history, we did not even know that interstellar space existed. Ancient peoples saw comets and called them omens or wandering stars. In the 1600s, scientists figured out that comets orbit the Sun and are part of our solar system. By the 1900s, we understood that stars are separated by vast distances, and we began to wonder whether anything ever travels between them. But it was not until 2017 that we spotted our very first confirmed interstellar visitor. That first visitor was called Oumuamua, a Hawaiian word meaning scout or messenger. Oumuamua was not a comet though. It did not have a tail. It was more like a dark, rocky asteroid, tumbling end over end as it sped through our solar system. Scientists watched it for a few weeks before it flew out of sight, leaving behind more questions than answers. Was it natural or artificial? Where did it come from? We will talk more about Oumuamua a bit later, but for now, just know that it opened the door. It proved that things from other star systems really do visit us, and if we watch carefully, we can catch them. The second interstellar visitor we found was called 2I Borisov, discovered in 2019 by an amateur astronomer in Crimea. Unlike Oumuamua, Borisov looked and acted exactly like a comet. It had a tail, it glowed with escaping gas, and it seemed completely ordinary except for its speed and trajectory. Studying Borisov taught us that at least some interstellar objects are just like the comets in our own solar system. They are made of the same stuff, they behave the same way, and there is nothing mysterious about them except where they came from. Now we have 3i Atlas, the third confirmed interstellar visitor, and the first one to give us a good look at an anti-tail. Each of these visitors teaches us something new. Oumuamua showed us that weird, unexpected things can come from interstellar space. Borisov showed us that familiar comet-like objects travel between the stars, and 3i Atlas is showing us the fine details of how interstellar comets release dust, how that dust behaves, and what it can teach us about the cosmic neighbourhood beyond our Sun. Here is something cool to think about. Before 2017, we had no confirmed interstellar visitors. Now, we have found 3 in just 8 years. That suggests interstellar objects are passing through our solar system all the time. In fact, some scientists estimate that on any given day, there might be dozens of interstellar objects somewhere between the orbit of Earth and the orbit of Neptune. Most of them are too faint or too far away for our telescopes to spot, and they zip through unnoticed. But as our telescopes get better and our sky surveys get more thorough, we are catching more and more of them. In the next 10 or 20 years, finding an interstellar visitor might become routine, like spotting a new asteroid or comet. The anti-tail of 3i Atlas stuck around for about 3 weeks before fading away as Earth's orbit carried us out of alignment with the dust disk. By early December 2025, the comet itself had also grown dimmer, moving farther from both the Sun and Earth. Professional astronomers and amateur stargazers alike took thousands of photographs during those few weeks, capturing the strange sight of a comet with a tail pointing the wrong way. Those images will be studied for years to come, analysed by researchers trying to understand everything they can about this rare visitor. Let me share one more fascinating detail that researchers discovered about 3I Atlas. By carefully tracking its motion and measuring how its brightness changed over time, scientists were able to estimate its size and rotation. The comet appears to be roughly 2 to 3 kilometers across, about the size of a small mountain. That is not huge as comets go. Some comets in our solar system are 10 or 20 kilometers wide, while others are less than a kilometer. So 3I Atlas is sort of medium-sized. It also seems to be spinning slowly, completing one full rotation every 30 to 40 hours. That leisurely tumble is typical for comets and asteroids, which are not perfect spheres but lumpy, irregular chunks of rock and ice. Knowing the size of 3I Atlas helps scientists estimate how much material it is losing as it heats up. Every time the comet comes near a star and warms up enough to release gas and dust, it gets a little smaller. After many close passes to stars over millions or billions of years, an interstellar comet like this one will eventually run out of ice and become just a dark, inactive rock drifting through space. Right now, 3I Atlas is still active, still shedding material, which means it has not been cooked by starlight too many times. It might have spent most of its life in the cold depths of interstellar space, far from any star, before wandering close enough to our sun to wake up and start outgassing. Before we leave 3I Atlas behind and explore its interstellar cousins, let's do a quick recap. This comet gave us a rare and beautiful anti-tail in November 2025. Created by heavy dust particles we saw edge on from Earth, scientists measured its speed, size, and composition, finding that it is similar to comets from our own solar system. It contains water, carbon dioxide, and carbon monoxide, the same basic ingredients found everywhere in the galaxy. And its visit reminds us that our solar system is not isolated. Objects from other star systems pass through regularly, bringing messages from the distant corners of the Milky Way. As 3I Atlas fades into the distance, heading back into the dark space between stars, we are left with a gift. We have learned a little more about the universe we live in, about how comets form and behave, and about the invisible highways that connect all the stars in our galaxy. The anti-tail was just a fleeting alignment, a brief moment when Earth, the Sun, and a visitor from interstellar space all lined up just right to show us something unexpected. But that moment taught us something real and lasting. The cosmos is full of travellers, and every once in a while they stop by to say hello. Oumuamua. The first messenger. Now let's turn our attention to the object that started it all, the very first confirmed interstellar visitor we ever spotted. On October 19, 2017, astronomers using the Pan-STARRS telescope in Hawaii noticed something strange. A faint point of light was moving quickly across the sky, too fast and on too strange a path to be a normal asteroid or comet from our solar system. Within days, scientists around the world were scrambling to observe it before it disappeared forever. They named it Oumuamua, which means scout or messenger from afar in the Hawaiian language, honouring the telescope in Hawaii that discovered it. Oumuamua was like nothing anyone had seen before. It did not have a tail like a comet. It was dark and reddish in colour, more like an asteroid made of rock and metal. But its path through space was clearly hyperbolic, meaning it had come from interstellar space and was on its way back out. The more scientists studied Oumuamua, the stranger it seemed. Its brightness changed dramatically as it tumbled through space, dimming and brightening in a repeating pattern. That told researchers it was not round like a ball, but long and skinny, shaped more like a cigar or a pancake. Some scientists estimate it might have been about 400 meters long and only 40 meters wide, like a cosmic skyscraper lying on its side, tumbling end over end. Here is where things got really interesting. When scientists calculated Oumuamua's path very precisely, they noticed something odd. The object was accelerating slightly as it moved away from the sun, as if something was giving it a tiny extra push. With a normal comet, this would not be surprising. When ice turns to gas and shoots away from the comet's surface, it acts like a little rocket engine, gently pushing the comet in the opposite direction. But Oumuamua did not seem to have a tail, or any visible gas escaping from it. So what was pushing it? One idea some researchers think might explain this is that Oumuamua could have been releasing gas so faintly that our telescopes could not see it. Maybe the object was covered in a layer of dark, rocky dust that hid the ice underneath. As the sun warmed it, tiny amounts of gas could have leaked out without creating a visible tail. That gas would still push on the object, causing the small acceleration scientists measured. Others doubt this explanation and have suggested different possibilities. Some wonder if Oumuamua could have been a fragment of a planet torn apart by its star, or even a piece of hydrogen ice that behaved in ways we have never seen before. A few scientists have even speculated, though most others strongly disagree, that it could have been an artificial object, like a piece of alien technology. To be clear, there is no good evidence that Oumuamua is anything other than a natural object. The idea that it might be alien technology comes mostly from the fact that we do not fully understand everything about it. And when we do not understand something, our imaginations can run wild. Science works by testing ideas carefully and only accepting the ones backed by solid evidence. So far, the evidence points to Oumuamua being a weird but natural chunk of rock and ice from another star system. Still, the fact that it behaved unexpectedly reminds us how much we still have to learn about the universe. Oumuamua moves so fast that scientists only had a few weeks to study it before it grew too faint and distant for even the most powerful telescopes to see. By early 2018, it was gone, a tiny dot of reflected sunlight disappearing into the blackness between stars. But the excitement it generated has not faded. The discovery of Oumuamua proved that interstellar visitors are real, not just theoretical. It showed us that telescopes and sky surveys are now good enough to catch these rare travellers if we watch carefully. And it inspired a whole new generation of astronomers to keep searching the sky, knowing that more visitors were surely on their way. Since Oumuamua passed through, scientists have been working on projects to build better tools for detecting and studying interstellar objects. One idea being tested is to create a network of telescopes that scan the entire sky multiple times each night, automatically flagging anything that moves unusually fast. Another project involves preparing spacecraft that could launch quickly if an interstellar visitor is detected early enough, chasing it down for a close-up look before it escapes the solar system. Imagine a robot probe catching up to an object like Oumuamua, snapping detailed photos, and maybe even landing on it to collect samples. That sounds like science fiction, but engineers are seriously designing missions like that right now. Oumuamua taught us humility. It showed us that even with all our knowledge and technology, the universe can still surprise us. It also taught us patience. We had been searching the sky for decades before finally catching our first interstellar visitor. Now that we know what to look for, we are ready for the next one, and the one after that. Each visitor will teach us something new, helping us piece together the story of how matter moves through the galaxy, how star systems are connected, and maybe even how common the ingredients for life really are. By Borisov. The familiar stranger. Less than 2 years after Oumuamua shocked the world, another interstellar visitor arrived, and this one felt almost comforting. On August 30th, 2019, an amateur astronomer named Gennady Borisov was using a homemade telescope at an observatory in Crimea when he spotted a fuzzy object moving across the sky. He reported it to the international astronomy community, and within a few days other telescopes confirmed what he had found. This was another interstellar visitor, the second one ever confirmed, and it was completely different from Oumuamua. This new object had a tail. It glowed brightly as gas and dust streamed away from it. It looked, in every way, like a perfectly normal comet, except it was not normal at all. It came from another star system. Scientists named it 2I Borisov, with the 2I meaning second interstellar object, and the Borisov honouring the man who discovered it. Unlike Oumuamua, which appeared without warning and disappeared just as quickly, Borisov gave astronomers plenty of time to study it. It was discovered while it was still far from the Sun, meaning scientists had months to observe it as it approached, swung around the Sun, and headed back out into space. Telescopes all over the world pointed at it. The Hubble Space Telescope took detailed images showing the glowing cloud of gas and dust around the comet's core. Spectroscopy instruments measured the light coming from the comet, breaking it down into a rainbow of colours that revealed what chemicals were present. What scientists found was reassuring and a little bit surprising at the same time. Borisov contained water, carbon monoxide, and other familiar chemicals just like comets in our solar system. But the amounts were slightly different. Borisov seemed to have more carbon monoxide than most comets we know, suggesting it might have formed in a colder environment or farther from its home star. This was the first solid clue that even though interstellar comets are similar to ours, they come from places with different conditions. Just like how someone from a different country might cook the same dish, but with slightly different ingredients, Comets from different star systems follow the same basic recipe but with small variations. One of the most exciting things about Borisov was watching it change as it got closer to the Sun. At first, the comet was faint and quiet, just a small icy lump cruising through the darkness. But as it approached the Sun and warmed up, it became more active. Gas started pouring off its surface faster and faster, forming a glowing atmosphere around the nucleus and creating a beautiful tail that stretched across the sky. For a few weeks in late 2019, Borisov was bright enough that experienced amateur astronomers could see it through backyard telescopes, a rare treat. Then, as it rounded the Sun and began its long journey back to interstellar space, it slowly faded again, growing dimmer and quieter until it vanished from view. Scientists also measured the size of Borisov's nucleus, the solid, icy chunk at the centre of all that gas and dust. They estimate it was somewhere around 1 kilometre across, maybe a bit bigger, about the size of a small town. That made it similar in size to many comets in our solar system, reinforcing the idea that comet-making processes are pretty universal. Whether you're orbiting a star 50 light-years away, or right here in our own backyard, if you clump together ice, rock and dust in the cold darkness, you get something that looks and acts like Borisov. One team of researchers used powerful telescopes to look for signs of complex organic molecules on Borisov. Organic molecules are not alive, but they contain carbon and other building blocks that life uses. Think of them like Lego bricks. Life is the spaceship you build, and organic molecules are the individual bricks you snap together. Scientists detected hints of organic compounds in the gas streaming off Borisov, which was not surprising. Comets are known to carry these molecules, but finding them on an interstellar comet confirmed once again that the ingredients for life are not rare or special. They are spread all over the galaxy, hitching rides on comets and drifting through space. Let me tell you about one particular study that grabbed a lot of attention. A group of scientists compared the dust coming off Borisov to the dust found on comets in our solar system. They looked at how the dust particles scattered sunlight, which tells you about their size and composition. What they found was that Borisov's dust was remarkably similar to the dust on comets that have never left our solar system. The particles were mostly small, fluffy grains made of silicate minerals, which are basically rocky materials like the sand on a beach. This was another piece of evidence showing that the universe uses the same basic ingredients everywhere. But here is the twist. Even though Borisov looked familiar, its orbit told a different story. By carefully measuring its path, scientists were able to work backward and estimate where it came from. The best guess is that Borisov was ejected from a star system somewhere in the direction of the constellation Cassiopeia, perhaps tens of light-years away. It might have been wandering through interstellar space for millions or even tens of millions of years before it stumbled into our solar system. During that time, it would have been frozen solid, colder than you can even imagine, drifting silently through the void. Only when it got close enough to our Sun did it warm up, start outgassing, and become visible to us. Think about that journey for a moment. Borisov was born around another star, perhaps one very different from our Sun. Maybe it formed in a disk of gas and dust swirling around a young star billions of years ago, just like the comets in our solar system formed in the disk that became our planets. Then, for reasons we can only guess, it was thrown out of its home system. Maybe a close encounter with a planet flung it into interstellar space. Maybe its home star had multiple planets, and their gravitational tugs gradually nudged Borisov onto a path that sent it wandering. Whatever the reason, Borisov left home and began a journey that would last longer than all of recorded human history. And by pure chance, that journey brought it through our neighbourhood, where we were lucky enough to see it. Borisov is still out there right now, moving farther and farther from the Sun, heading back into the cold darkness between stars. In a few thousand years, it will be so far away that no telescope on Earth could ever see it again. Eventually, maybe in a few 100,000 or a few million years, it might wander close to another star and warm up once more. If there are astronomers around that star, they might spot Borisov and wonder where it came from, just like we did. It is a cosmic traveller, carrying its secrets from star to star, connecting the galaxy in ways we are only beginning to understand. The discovery of Borisov did something important for science. It turned interstellar visitors from a one-time fluke into a pattern. Oumuamua was weird and unexpected, which made some people wonder if it was a mistake or a misunderstanding. But Borisov was clear, straightforward, and exactly what you would expect an interstellar comet to look like. Together, these two objects proved that interstellar visitors are real. They are different from each other, and they happen often enough that we should expect more. That realization has energized the field of interstellar object research and set the stage for discoveries like 3I Atlas. Cosmic highways and galactic wanderers. Now that we have met the 3 confirmed interstellar visitors, Oumuamua, Borisov and 3I Atlas, let's zoom out and think about the bigger picture. Where do these objects come from? How do they end up travelling between the stars? And what does their existence tell us about the galaxy we live in? These questions take us on a journey through space and time, connecting the stories of individual comets to the grand history of the Milky Way itself. Every star system in the galaxy is like a little island in space. Our Sun, for example, has 8 planets, countless asteroids, millions of comets, and who knows how many smaller chunks of rock and ice orbiting it. Most of that material stays put, bound to the Sun by gravity, going around and around for billions of years. But sometimes things get thrown out. Imagine you're on a merry-go-round at a playground, holding onto a ball. If you let go at just the right moment, the ball will fly off into the distance. Something similar happens in star systems. When a small object like a comet or asteroid passes close to a big planet like Jupiter, the planet's powerful gravity can slingshot the object, flinging it so fast that it escapes the star's gravity and goes flying into interstellar space. Scientists think this happens all the time, in every star system, all across the galaxy. Our own solar system probably ejects thousands or maybe even millions of comets and asteroids into interstellar space every year. Most of them are too small for us to notice, but over millions of years the numbers add up. Right now, drifting through the space between stars, there are probably trillions and trillions of small icy and rocky bodies that were once part of some star's family but got kicked out. These cosmic wanderers, sometimes called rogue objects, make up an invisible population filling the galaxy. We cannot see them because they are dark, cold, and spread out over unimaginably vast distances. But every once in a while, one of them happens to pass through our solar system, and if we are watching carefully, we catch it. Here is a wild thought. For every interstellar visitor we detect, there are probably thousands or even millions that pass through unnoticed. Remember, space is big. Really, really big. Even something as relatively close as the orbit of Neptune is billions of kilometers from Earth. An interstellar object the size of a house or even the size of a mountain could zip through the outer edges of our solar system, and we would never know. We only catch the ones that come close enough to the Sun to become bright, or the ones that happen to pass near Earth where our telescopes are watching. As our telescopes improve and our sky surveys get better, we will start catching more of these visitors, and the trickle of discoveries we see now will turn into a steady stream. The paths these objects take through the galaxy are shaped by gravity. Imagine the Milky Way as a busy city with millions of cars driving in different directions. Most of the cars stay on the roads, following predictable routes, but every now and then a car takes a wrong turn, leaves the city entirely, and ends up driving through the countryside. That car is like an interstellar comet. It is no longer bound by the structure that shaped its path. It is free-floating, moving in whatever direction its last encounter sent it. Over time, gravity from passing stars and the galaxy itself will bend its path slightly, but mostly it just coasts, following the momentum it gained when it was ejected. One idea being tested is that some interstellar objects might not have been ejected from star systems at all. Instead, they might have formed in the space between stars, in giant clouds of gas and dust where stars are born. These clouds, called molecular clouds, are cold and dense enough that small clumps of material can sometimes stick together and freeze into tiny comets or ice balls without ever joining a star system. If that happens, those objects would be truly interstellar from the very beginning, never belonging to any star. Scientists are still debating whether this process is common or rare, but the discovery of visitors like Oumuamua, Borisov, and 3I Atlas is giving them clues to work with. Let's talk about what these interstellar visitors can teach us about the diversity of star systems. Every star is a little different. Some are hotter and brighter than our Sun, some are cooler and dimmer, some are young, just a few million years old, while others are ancient, older than the Sun itself. When planets and comets form around these different stars, they reflect the conditions of their birthplace. A comet that formed around a hot, bright star might have different chemicals than one that formed around a cool, dim star. By studying interstellar comets like 3I Atlas and Borisov, scientists can sample the variety of comet recipes the galaxy has to offer, giving us a window into environments we could never visit ourselves. One fascinating possibility scientists are exploring is whether interstellar comets could have played a role in spreading life, or at least the ingredients for life, across the galaxy. This idea is called panspermia, which means seeds everywhere. The basic concept is simple. If comets carry water, organic molecules, and maybe even microscopic life, and if those comets travel from star to star, then they could act like delivery trucks, dropping off their cargo at different planets along the way. When a comet crashes into a planet, it does not just make a crater, it also deposits whatever it was carrying, including all those interesting chemicals and possibly even living microbes frozen in the ice. Now, most scientists doubt that actual living organisms could survive the journey through interstellar space. The radiation out there is harsh, the cold is unimaginable, and the trip takes millions of years. But organic molecules, the building blocks of life, are much tougher. They can survive freezing, radiation, and the vacuum of space. If interstellar comets have been crisscrossing the galaxy for billions of years, delivering organic molecules to countless planets, then maybe life did not have to start from scratch on every single world. Maybe the ingredients arrived pre-packaged, courtesy of wandering comets like 3I Atlas. This does not mean life itself travels from star to star ready-made. It just means the raw materials might be spread around more easily than we thought. Life still has to assemble itself from those materials, which is a hard and mysterious process we do not fully understand yet. But knowing that the ingredients are common and that interstellar comets can deliver them to new places makes the idea of life elsewhere in the galaxy seem a little more likely. Every interstellar visitor we study adds one more piece to that puzzle. Before we wrap up, let's think about what comes next. The discovery of 3 interstellar visitors in just 8 years suggests we are on the edge of a new era in astronomy. Soon, powerful new telescopes like the Vera Rubin Observatory will come online, scanning the sky more thoroughly than ever before. These instruments will catch fainter objects, track them more accurately, and give scientists advance warning when an interstellar visitor is approaching. Instead of scrambling to observe these objects in the few weeks before they disappear, astronomers will have months or even years to study them, gathering far more data and answering questions we cannot even ask yet. Some researchers are already planning missions to intercept interstellar visitors up close. Imagine a small, fast spacecraft sitting quietly in orbit, waiting. When an interstellar object is detected heading our way, the spacecraft launches, matching its speed and trajectory, flying alongside the visitor for weeks or months. It could take high-resolution photos, measure the temperature and composition of the surface, maybe even deploy a tiny lander to touch the object and scoop up samples. That kind of mission would revolutionize our understanding of interstellar space, turning these brief glimpses into detailed, hands-on investigations. The anti-tale of 3I Atlas, strange and beautiful, is just one small chapter in a much larger story. That story is about connection, about how the galaxy is not a collection of isolated islands, but a vast interconnected web where matter flows from star to star, carrying information, chemistry, and maybe even the seeds of life. Every comet that wanders through our solar system is a messenger from some distant place, a traveller with a story to tell. We are only just learning to read those stories, but every new visitor teaches us a little more. As 3I Atlas continues its journey back into the darkness, its brief anti-tale now faded and gone, we are left with wonder and curiosity. Where did it come from? What star did it orbit billions of years ago? What other planets might it have passed on its long journey? We may never know the answers to those questions, but we do know one thing for certain. The universe is full of surprises, full of objects that do not follow the rules we expect, full of beauty that appears without warning and vanishes just as quickly. And as long as we keep watching the sky, keep building better telescopes and keep asking questions, the universe will keep answering. The anti-tale returned for a brief moment in November 2025, pointing at the sun like a cosmic arrow, reminding us that even in the emptiness of space there are highways and travellers, connections and stories. 3I Atlas came from somewhere out there, and someday it will arrive somewhere new, carrying its cargo of ice and dust and mystery to another corner of the galaxy. Until then, we have the gift of knowledge, the understanding that we are not alone in the universe, not isolated or special. We are part of something much bigger, a galaxy full of wanderers and wonders, and every day we get a little closer to understanding what that really means.